It's a beautiful day here in Tällberg, Sweden. We have gathered 500 of us from all corners of the world, from all walks of life. Many are scientists. We're here to take stock of the evolution of the situation for the planet. We are taking stock. We are defining what we call the planetary boundaries that we, the humans, should not transgress on such crucial issues as water, oceans, forests, and of course the atmosphere, global warming. Many analyses are represented here. Some are more optimistic, some are less so. One is Professor David Wasdell, a leading British scientist. He has gathered his material to tell you a worrying, very worrying story. I think this story is important to listen to. And for you, it's important to take your decision on how you want to react and how you should react, how you should act in relation to his story.
Well, good morning to you all, and thank you so much for the invitation to Tällberg 2008 and to the science workshop that preceded it. I'm immensely grateful to you, Boo, for the invitation and for making this possible. When Boo briefed me for the presentation today, he asked me, in fact, to be radical. I wasn't quite sure I believed my ears when he said that, but I checked it out again 48 hours later. He said, yes, that's exactly what I mean.
Stay radical now.
He's always radical.
Stay radical.
Yeah.
I think the boundaries of tolerable radicality have to do with the anxiety states of scientists who dare not put their head above the parapet and risk being wrong in public. So maybe it's something about courage and radicality go together, right?
Now, to me, the word radical probably means getting down to the root of the problem. Say it as it really is. And I will do that to the best of my ability. One of the things we need to be aware of in climate science is that there is a time delay between original research and publication of about 3 years. Original ideas come into being in the researcher's mind or from the data or the analysis or the modeling, and then that gets written up with a team into a paper that goes through a whole series of reviews. That then gets presented for publication in an international journal. They may or may not accept it or put it on hold for a few months. Then it gets sent out to a set of anonymous reviewers, comes back, maybe re-edited, maybe sent out again, comes back, accepted, and then published perhaps 2 editions later. Then it's in the public domain. Oh, and then the Intergovernmental Panel on Climate Change is able to pick up the material and put it through its 18-month to 2-year review, assembly, analysis, editorial processes, out for peer review on that, back in again, out for another peer review on that, back in again, out to review through the governmental agents, back in again, and publication. So by the time the Intergovernmental Panel on Climate Change was published in February 2007, it was about 5 years out of date. This is a real problem when the pace of change in the climate system is moving faster and faster and faster. It is now outpacing the delays in the publication system. The climate science group that convened for the 2 days before the forum, as some of you here will know, focused on the tipping points that we dare not cross, tipping points that push us into change that is intolerable for human civilization. The workshop was based on peer-reviewed material. And although perhaps 2 to 3 years in advance of the Intergovernmental Panel's work, it was still about 2 to 3 years behind the leading edge of current research. And my task today is to bridge the gap from the foundation that Johan Rockström laid and the others laid in that science workshop, and to bridge the gap from that platform to today's leading edge, some of which is work in hand, some of it only emerging in the last 2 or 3 weeks. Therefore, it's rough-edged, it's workshop level, some of it will be polished and corrected. But I think it's important that you here today have the best possible chance to see where the leading edge is and where it's going. Planet Earth, we have a problem. You know, back in April 1970, in the Apollo space program, on the 13th of the month, there was an explosion on Apollo 13. And perhaps those of you who are old enough here, and some of you are, as I am, can remember being glued to the television as the saga unfolded. And those laconic words from Jim Lovell, Houston, we have a problem. Telling me they had a problem. Gene Kranz, who was the mission controller at the time, reflects in his storytelling of this. For about the first 15 minutes, we said it's not a problem. This is a computer glitch. There's no problem out in space. We'll get this fixed. No problem. And it took them 15 minutes of precious time to realize there really was a problem, that the moon landing as a mission had to be aborted. The task now was survival. And that changed the whole function of the mission. Today, Planet Earth is the space capsule, and Planet Earth is Houston control. We're all in it together. And it's taken us more than 15 years to think that this may not just be a bit of a glitch, that technologically we can patch together and no problem. Planet Earth, we have a problem. And that problem is specifically the role of the accelerating feedback dynamics that increase the pace and severity of climate change and drive it outside the predictions of most of the models that we have running at the moment. They tend to work on more linear processes, more equilibrium processes that are appropriate when looking at the ancient changing patterns of weather and climate. But in this situation, the change is running faster and outside the prediction parameters of our models. So it's to the exploration of feedback processes and their effects on the climate that I want to present this morning as radically as I can. Let's start at the very beginning. The whole sense that the impact of the human species on the climate has really been absolutely minimal through this early stage. And we have seen from the early development of humanoids and then the first moderns and through here, really a very small population held in balance within the natural environment until we begin to move to around the 1600s. Trading base bringing in resources from other parts of the world, and then the discovery of fossil energy, energy from yesterday's sunlight, buried in the darkness of the underworld, brought to the surface and liberated for today's generation to benefit from yesterday's sequestration of atmospheric carbon. And that set off an energy input that escalated the population, which required more energy, which escalated the population, which required more energy, which escalated the population. Very interesting. This is taken from Al Gore's slide set, and I'm very grateful to him for permission to use it. But it is very interesting. You see here that the scale gets wider and wider from many, many thousands, as it were, per unit back there. And then we get to 1,000 in this unit, and here, and then this is 150 years. If you kept the same scale all the way around, this would simply go vertical. It's not a hockey stick, it's a right angle. And it's interesting, the scale pulls up, makes it look fairly benign as an explosion. It's a swarm, it's a plague. And by the way, everybody stops at the top of this curve. Do you notice that? I had a word with Dennis Meadows, who was responsible for the updating of the Club of Rome's reports on the limits to growth, and asked him why they had missed out the death rate curve from their work, when Jay Forrester, who was the supervisor of the whole project, always put the death curves in, the death rate curves. He never gave me a proper answer to that, but I'll explore this with you. When a population curve like this reaches a peak that is such an extraordinary explosion, and I heard someone in the science group say, and it stabilizes at about 9.6 billion, give or take. It doesn't stabilize. Most curves like this go into an immediate collapse again, and then they can either come down to a minimalist population or oscillate. Going up to a smooth peak and then stabilizing at the peak population is very, very rare. So we've got problems ahead. Anyway, oh, by the way, the energy use per head has also increased during this time. So if we plot the energy available and energy used by this swarm, it goes way off the top of the screen. And of course, the more energy we use, the more pollution we put out, the more pollution we put out, the more carbon dioxide there is in the atmosphere, and the more problems we have with climate. Pollution, what you see is not what I'm talking about. It's what we don't see in the pollution that does the damage. The particulates wash out again quite quickly. The carbon dioxide, the sulfur gases, the nitrous gases stay in the atmosphere. And those are the greenhouse gases, of course, that create the heating. What's the history? Many of you will know the pattern of the change in carbon dioxide from the warmer interglacial to the icy glacial conditions. Warmer, icy, warmer, icy, warmer, icy, warmer. And then we got going. You would expect this to be just dithering around like this and going down again as we move towards the next cooling period slightly. Although actually there is a window of about 30 to 50,000 years in this process in which the climate stays fairly stable for the next significant period. It's quite unusual in the sequence. But then we got to Earth, and what we call the anthropogenic, it's the what we done. I love the scientific terms that you can have to translate into common English. The anthropogenic output of carbon dioxide takes us up to where we are today, 2001, about 380 parts per million of carbon dioxide in the atmosphere, which is the way the scientists measured, where we're at today, 2008. If you add on the effects of the other greenhouse gases that we put up there, about, I can't even reach up here, it's about 445, 450 parts per million. If we go on doing what we're doing, by the end of the century, it'll be virtually off the scale. Oh, and that's not counting bringing in the output from the burning forests of the Amazon and the other great tropical forested areas, or the boreal forests dying back with beetle attack and great forest fires. Oh, and the release of methane from layers under the sea and from under the thawing permafrost in the tundra. So greenhouse gases go right off the scale. There is nothing in the last 400,000 years of paleoclimate records that gives an inkling for this kind of behavior. Do you remember when you opened up this forum, we had the picture of the man standing on the brink of the Victoria Falls, looking into a pool at its edge with his back to the great abyss, looking back upstream. Now, if climate scientists only model what happened back upstream, they have no evidence for the huge discontinuity, the tipping point of the Victoria Falls. And if they argue from the back downstream or up towards the source of the river, you will have no ability to predict what happens next. And if that man is looking back up the Zambezi and confidently walks backwards into the future, looking at the past, there will come a point where he tips into accelerated catastrophe, and then there's only a tiny window of intervention when he can regain his balance and come back again. We're at that point. I want you to think global, to treat the Earth as a whole in its relationship to its environment and space. So here goes. We know that increase in the concentrations of greenhouse gases raises the efficiency of the insulating envelope and reduces the net global radiation. If you look at those red little arrows pointing out that says the radiation we give out into space from the Earth just balances the radiation we receive from the sun, and that balance is what maintains the conditions for life. We reduce the amount of radiation going back. That means that temperatures start to rise at the surface, and that means provided there is just a single step increase in greenhouse gases, then slowly, as the temperature goes up, radiation goes out again, and we recover equilibrium. Sadly, it's not like that. We have accelerated the accumulation of greenhouse gases. It's not just a set step increase. It's going up exponentially. So the radiation levels are decreasing. So the heating is increasing. Oh, and by the way, feedback dynamics are also pushing the system even further out of balance and pushing us towards a hotter and hotter Earth response. Now that's the phenomenon we're going to look at in depth. So here we go. Problem, feedback dynamics, and the acceleration of climate change. Ready to go? Okay, we're going to change the way we look at it. Let's look at what actually makes climate change happen. Here we have, we're used to this, aren't we? Increased carbon dioxide concentration drives the heat engine. You know, scientists call it radiative forcing. That doesn't translate into anything that most of us understand. They know what they're talking about. I know what we're talking about, but most people don't. Radiative forcing is global heating. It's the heat engine that drives the change. The temperature is the outcome of the heat engine. It's like you have a big cauldron of water on your gas stove. You turn the gas up, that's the heat engine. The thermometer goes up slowly as a response. Right, this is the gas light. That's the thermometer. So, increased carbon dioxide drives the heat engine. So does methane concentration drive it. Other greenhouse gases drive it. There are effects from aircraft condensation to Earth, the contrails, the aerosols, the particulates in the atmosphere. They affect the heat engine. So, of course, there's the reflection from surfaces on the Earth, particularly snow and ice, savanna, desert. The difference between water and trees and mountains. And then finally, the cloud effects, which are so difficult to model. Light reflects from the top surface, but clouds tend to act as an extra blanket and keep you warmer as well. So they go both ways. And it depends on the height of the clouds, whether they're ice particles or water droplets and the thickness of them and the size of them. It's an immensely complicated modeling area. The energy that comes in from the sun is the driver, and there are some, obviously that's what helps the heat energy. There's a small amount of energy from what we call geothermal energy at the center of the Earth, which provides a little heating at the surface. But it's very small, and we can ignore it for the sake of today's work. Okay, so that's what drives climate change. Now we bring in the feedback processes. What we've done here is create a series of clusters of feedback. Each cluster is driven by one particular phenomenon, effect in the climate of behavior, and has its own effect on a particular field of behavior. So, for instance, the cluster feedback group 1 is driven by increased concentration of carbon dioxide and affects the increase in carbon dioxide. All the rest are driven by temperature, a bit like this. So there we have the cluster F1 driven by and affecting on carbon dioxide. All the rest of the feedback processes are driven by rising temperature, and then they in turn act on the driving processes that turn the heat up, which puts the temperature up, which in turn drives the drivers, which puts the heat up, which puts the temperature up, which drives the drivers, which puts the heat up, which puts the temperature up, and we have a global feedback process. What they do? Now we could look at some of those in detail, and back behind this presentation is a 3-day seminar, so I'm going to be a little bit briefer than that this morning. But we could quite briefly look, for instance, at the methane cycle. And here we have methane that emerges from human activity, from plants and animals, bacteria, and methane released from store. That summed up gives the methane emissions, increases methane concentration in the atmosphere. In the atmosphere, methane slowly breaks down into carbon dioxide and water vapor. Carbon dioxide adds to the CO2 stock, but the methane is a very powerful greenhouse gas and puts the heat engine up and puts the temperature. Now there's a feedback cluster in the methane cycle which operates like this. It's driven by temperature, and the warmer the temperature gets, the greater bacterial activity and the increased methane production. This we already see. More methane production, more global heating, temperature goes up, bacteria love it even more methane, but we've got there. That's what feedback's all about. The next one, tundra permafrost, those great areas of the icy waste with fossil ice left over from the last ice age deep underground, and the surfaces which just thaw a little bit in the summer and freeze again in the winter. Today, they are thawing deeper and deeper and deeper. We have an area about the size of France and Germany combined in Siberia now engaged in quite rapid thawing. And in that permafrost are trapped deposits of methane and deposits of biological material which the bacteria then get out, and we get release of methane. More methane goes out, more heating, temperature goes up, more thawing, more methane, and so forth. And then the really big one, there is about 3 times the amount of hydrocarbon energy stored in methane clathrates, as they call them, the frozen lattices of methane stored in the shallow seas at appropriate temperature and pressure conditions. 3 times as much hydrocarbon energy in that methane store as in the total store of coal, oil, and gas combined. That's a lot of energy. As the seas start to warm with global warming, that methane can start to release. Oh, it's not going to happen for decades. You don't have to worry about it. Well, actually, NASA reported in a confidential email to me in February 2007 that the first methane clathrate release had been detected off San Diego in October of the previous year. But please don't pass this on because the Bush administration might not be too pleased. Last December, and in the months that have followed since, we know that the NASA satellite monitoring has shown plumes of methane coming up from the shallow seas off the north of Siberia as the clathrates in that continental shelf begin to move. Decades ahead. We have already activated the methane bomb, as they call it, but it's a slow burn. The oceans warm very slowly and mix down to the seabed, and then the methane comes up, and then the temperature slowly responds to that. So it's a slow but inexorable cascade feedback process. gives you some idea. I'm not going to go through all the details of all the ones there, but it gives you some idea of the feedbacks and the mechanisms behind them. Oh, by the way, heating is applied to the whole Earth system, and it's vast. I mean, it takes time to bring a cauldron of water to the boil, doesn't it? Turn the heat up full, and the temperature goes very slowly up. The bubbles form on the bottom. Now, the inertia of the world is vast, and the heat engine has to do this. So here we go. Heating from all sources drives the energy that slowly puts the temperature up. It has to heat ocean, it has to heat the land mass. It heats ice before it starts to melt. It heats the atmosphere. Melting of ice takes a lot of energy before the temperature changes at all. It's a phase change from solid to liquid. Oh, and evaporation of water, increased water vapor in the atmosphere, is also a phase change that takes a lot of energy. So the heat goes through those processes before it starts to make a difference to the temperature. And if we look at changes in temperature and base our strategic policies on observed effects of temperature rise, we have missed the point on global heating. What matters is what's happening to the heat engine, and strategic policies geared to observation of current effects are strategically disastrous in engaging with the system's behavior. Oh, and by the way, just to complete the picture, there's another feedback cluster hiding here. The hotter it gets, the less inert the system is, and the faster it gets hotter. That one's only been in the understanding of our science domain for the last few months. So there we are, and we can put in that final feedback cluster. Now that encapsulates the feedback and driver system of the global climate behavior. So, let's summarize. Most of the systems known to affect climate change are now in net positive feedback. Each feedback mechanism accelerates its own specific process. But as a whole, this complex adaptive feedback system consists of an interactive set of mutually reinforcing subsystems. Isn't that wonderful? What it means is this, that the output from one feedback changes the temperature a bit faster. That feeds into all the other feedbacks, so they reinforce each other. That's an unstable system. It can move very quickly indeed. It's what we call a second-order feedback system. Remember presenting this material for the first time, to the European Environment Agency in Copenhagen, February 2006, I think it was. And Jackie McGlade, the director of the agency, and I were talking afterwards, and I said, I don't think we're going to see this second-order feedback system operating for a long time because temperature rises very slowly. She said, David, this is a complex adaptive system with feedback on feedback. This can go very quickly indeed. Jackie is one of the members of the Resilience Alliance that looks at exactly this stuff at a high level of mathematical precision. There are only a very few mathematicians in that able to do this kind of work. She's one. So I went on. And I changed my presentation. Anyway, Bo, you asked me to be radical and say it how it is, so here's how it is. Evidence for that from Dennis Bushnell, who, in parallel, of course, with James Hansen, Dennis Bushnell is chief scientist at the Langley Research Center of NASA. His email of the 12th of January last year reported on the phenomenon that were being observed across the world. And he said, warming is accelerating greatly, and especially recently. Oh, and that was before the anomaly of 2007, the massive loss of ice from the polar area. So the evidence of acceleration is already in the public domain. That moves us on not just to dealing with the effects of acceleration, but moving towards what we call a tipping point, where things really run out of control, not just smooth acceleration, but behaviors that go unstable. So here we introduce the work of James Hansen from the Goddard Institute. Again, same sort of date from James' publication. The Earth's climate, remarkably sensitive to global forcing. Positive feedbacks, accelerating feedbacks predominate. And that allows the whole planet to be whipsawed between states. It's what we call a metastable system. Small pushes lead to big movements. Recent greenhouse gas emissions place the Earth perilously close to dramatic climate change that could run out of our control. Great dangers for humans and other creatures and to the whole life support system of planet Earth. You see, we really do have a problem. So we're going to look at this issue of tipping points, and this takes us into the next station, beyond the tipping point. There have been 5 major extinction events in the geological history of the Earth, caused by massive volcanic eruptions or huge lava flow, or in 1 or 2 cases possibly, major asteroidal impact. And it's interesting here in Tailberg, as we sit on this hilltop, which is part of the frozen shockwave stabilized in granite from that great impact of a meteor, the crater of which forms the basin of the lake, whose beauty we admire on a daily basis. This was a local extinction event, believe me. But the major ones in Earth's history have meant shock jumps in carbon dioxide, and that pushes the system away from equilibrium and into very rapid change. Typically, they have wiped out 80, 85, 90, 95% of life on the planet. It takes many, many thousands of years for the geochemistry to recover, and several millions of years for the biological species to recover any sense of niche filling. What's a tipping point? Well, here's a lovely illustration from Brian Walker of the Resilience Alliance from Australia, a tipping point of bifurcation, and it's illustrated by a basin of familiar behavior which varies a bit, but it's held by this containing area here, and the behavior of the climate can move around within that contained. As the positive feedbacks build up, they can push that behavior over the watershed and down into another basin, a hotter Earth scenario, from which it's very difficult to recover back into the stability of the previous one. That's a tipping point. See how this goes. By the way, what I'm going to do next, actually, is take a line from about here, up over the watershed and down into the next basin. You got the idea? So that's going to be a cross-section through there. It's much easier to work with. It's like the watershed between 2 valleys. You come up the path, over the top, and down into the next valley. Here it is. The original stable state equilibrium, the inflection point where positive feedbacks begin to have an effect on the containment, the unstable equilibrium where positive feedbacks and the containing, damping feedbacks just balance out, and then beyond that, the accelerating feedbacks push the system towards runaway change. Contained runaway, but it, for our purposes, in human life terms, it's runaway. Onto that, I want to introduce the concept of the critical threshold. Critical threshold is a point beyond which the power of the accelerating feedback overwhelms the human power to intervene and restore the system to equilibrium. There's a limit beyond which we dare not go. Oh, in terms of costs, of course, and the energy required to make the difference, it's the point towards which the cost of restabilizing the climate doesn't just go on increasing or going up slowly, as in the assumptions behind the Stern report. It goes up vertically to infinity. Beyond that, it would cost the Earth and still not restore the system to equilibrium. Let's illustrate it. Along the bottom axis, the power of positive feedback relative to what we can do about it. So in the early stages, easy to restore the system to equilibrium. Feedback builds up, more difficult. Feedback reaches the critical threshold here, just on the limit of everything we can do. Beyond that, nothing we can do. It costs the Earth. Costs up that axis. And this is what I mean by asymptotic increase as we reach the critical threshold. The costs escalate to infinity as that threshold. That's the point of no return. If we superimpose the two graphs, if we bring the equilibrium graph and the critical threshold into the same diagram, it looks like this. We are fairly confident that we've passed the unstable equilibrium and are somewhere on the downslope. The critical threshold beyond which we have no hope whatsoever of pushing the system back into stability lies somewhere, we hope, ahead of us. Costs escalating rapidly of making the intervention that is needed. And we've delayed 15 years already to make that intervention. We dare not delay longer. It costs more and more and more to make the intervention. The effects of climate change are building up. Resources have to be put into recovery, adaptation, insurance, social conflict, energy sources, food, water. The resources available to make the intervention decay as we approach this threshold. So acting now is critical. Okay, let's put in a time dimension to this, shall we? And this really gives a very good illustration of it. Here is the stable climate equilibrium. The ridge represents the tipping point beyond which the system moves towards runaway. The wall represents the critical threshold that we dare not cross if we are going to avoid the sixth extinction event. So we can go for a walk in this valley system, and we have moved slowly over our history up over the hill, and in our current continued business as usual, are heading for disaster. The Kyoto arrangements and the current set of negotiations change the path a little, but go straight on through the wall. What is required is an intervention that moves us back, skirting the wall, and comes back over into the state of stable equilibrium. Let's summarize that. We're now in the early stages of runaway climate change. There's no naturally occurring damping, braking system to stop it happening. It's our job. Strategically, we have to generate a negative feedback intervention of sufficient power to overcome the now active feedback processes. And by the way, in the time that it takes to make that happen, temperature goes on going up. And the temperature going up brings in more feedback. So our intervention has to be able to control and damp the temperature-driven feedback during the process of intervention. That is a very difficult task. Apollo 13 faced a similar situation. Climate stabilization is the strategic imperative for tomorrow's world, and tomorrow starts now. You know, most of us find that when we're faced with a problem of this magnitude, it leaves us feeling almost overwhelmed and numb. And I think it's terribly important that we get some understanding of a way ahead that can see us through the crisis with some realistic degree of hope. So, Bill, I don't know if it'd be in order this morning, but I would like to bring to you the best shot we have at a possible solution to go through this crisis and to begin to look at the way ahead rather than just leave you hanging on the end. Would that be okay? Yeah, I know I'm stepping over my time limits, but I really feel that this could be quite important for our whole process together. Thank you. Okay, I'll do that, and I'll be as brief and sharp as I can be. Let's have a go. We've seen the reality for what it is. We've turned round on the lip of the Victoria Falls and seen the abyss below. Now, what do we do? How do we get back to safe water? Well, we're going to start by looking at the whole concept of the heat engine, the radiative forcing that is driving the problem. Global heating is the gap between the energy received from the sun and the energy radiated back into space, normally held in equilibrium because of our intervention, significantly out of kilter. So it's been behaving like this. The energy driving global warming has been accelerating, actually more than exponentially. That's our problem. Where does it come from? From a series of greenhouse gases. The carbon dioxide, particularly, has made the most difference. We measure the heat engine in terms of watts per square metre on the Earth's surface. So carbon dioxide has added about 1.5 watts per square metre to the heating. Methane has added about 0.8. The nitrous oxides from fertiliser use have added some. The chlorofluorocarbons, the ones that attack the ozone hole, have added some as well. They've stopped growing from the success of the Montreal Protocol that limited their use. They stay up there an awful long time. So by 2000, we had about 2.5 watts per square metre from the greenhouse effect. And here's Jim Hanson's updating of that in 2005. And you'll see there's that 1.5 watts from carbon dioxide, 0.5 watt from methane, some from the chlorofluorocarbons. Can you say chlorofluorocarbons quickly with your false teeth in? I couldn't. Ozone, low-level ozone, basically from transport, gives more than the chlorofluorocarbons. Oh, and black carbon, sooty particles in the atmosphere, warm the atmosphere. They also settle on snow and ice and decrease the amount of light that is reflected back from them. So black carbon is adding a significant amount to the heating. And then there's the reflection from particulates in the atmosphere, what we call global dimming, with the double effect, both from the particulates themselves and the clouds that they lead to formation. So we have about just over 2 watts dimming from that effect. A little bit of change from change in sun's activity during the period from 1750 to 2000. A little bit of increase in sun. But in fact, did you know that the solar output, the energy we receive from the sun, has decreased since 1987, when most of the global warming has occurred? So keep that in your mind when people say it's all to do with the sun's radiation. By the way, if we add these last 5 elements together, the black carbon, the aerosols, global dimming, and the solar activity, that's about -1 watt per square metre. You put that into the memory bank and hold it for a minute. Historically, right, we have virtually no change in global heating. It stays at 0, up to the point of the onset of the Industrial Revolution. By 2000, there's that carbon dioxide gone to 1.5 watts per square metre. Bring it up to date, that's up to 2007, it's slightly more today. We can add on the effects of the other greenhouse gases. Then we have to add in the effect of water vapour feedback. Water vapour is a very powerful greenhouse gas, which we tend to ignore most of the time. It accounts for about half of the greenhouse effect. But when temperature starts to rise, water vapour in the atmosphere increases, and that accelerates the rate of heating. Water vapour adds about 1 watt per square metre per 1 degree rise in temperature. So we've had about 0.8 of a degree rise in temperature, so that's an extra 0.8 of a watt per square metre. And then we add on a little bit extra for the change in the albedo effect, the reflection from ice and snow. As the ice fields have shrunk, the snow fields have shrunk and lasted less time. So that's about 4 watts per square metre. It's not a lot, you say. Not a lot. We have to take off from the memory bank brought in 1 watt per square meter from global dimming. And by the way, as the temperature increases, we radiate more into space, so that decreases the heat engine. We've just been able to do the first calculations of that, so we're taking off another watt for our current temperature rise. That gives us about 2 watts per square meter of the heat engine. I don't think watts per square meter mean very much to you. But tonight we have the final of the European Football Cup with Spain against Germany. The result will be interesting to see. But there's about the equivalent of 8 kilowatt fires on the football pitch, which you'll be seeing tonight. Add that up to a global total, and you're looking at about 1 million gigawatts. Mind-blowing numbers, aren't they? 1 million gigawatts over the whole Earth. Or if you want to put that into kilowatt fires again, that's 1 trillion, 1 million kilowatt fires. That's some heating. You know, sometimes somebody just absolutely deflates your bubble in a presentation like this. Somebody once said to me, you know, they're not using kilowatt fires anymore, it's all central heating. And I said, oh, for goodness sake, I have to think of something else. But this will do for now. Gives you an idea. Oh, by the way, the heating is increasing by about 25% per decade. Oh, and that rate of increase is increasing. Climate stabilization means reducing that heating to 0. Otherwise, the temperature goes on going up. How do we do it? Well, just like that. Just like that. We have to make an intervention that slows the rate of heating, stops it, brings it back down again. If we simply bring it down to the 0, to an equilibrium, we will have succeeded in stopping runaway change. We will have stabilized the planetary climate, but at a cost. Because the temperature increase at stabilization point will still lead to catastrophic impacts and tipping points and chaos in many of the climate systems. So we also have to go through some period of global cooling into negative radiative forcing, as they say, to make certain the temperature doesn't exceed tolerable limits. And then we come back to thermal equilibrium. That's the overall strategy. It is not, of course, the strategy being addressed through the IPCC processes, the Montreal protocols, and so forth. They are addressing a climate agenda that is way out of date from the reality of the system as we know it today. How on earth can you... Remember we saw that the images from James Lovelock in the video interview in the forum just a couple of days back now. And James was saying we've passed the tipping point in the global system, and there's nothing else we can do about it. There are going to be some surviving species, but basically it's the end. I know James fairly well, and I've sat actually in that chair in his study that we saw him speaking from. And we had some time together. James's understanding of the climate system is brilliant. His understanding of Gaia interactivity and the life support system, supreme, a genius. And by the way, he's a technical genius as well. Some of his inventions are currently on Mars, measuring atmospheric chemical composition. But James is a strange animal, totally unwanted child, for whom social interaction has always been difficult. And when Boo described the almost paradisical house that he has in this lovely hidden valley in Devon, it's a retreat from humanity. James's being in favor of the nuclear option comes actually from his rage at the thought of a wind farm being on a hill that he could see. That's the motivation. And any sense of invasion of his deep, secluded private space brings out a reaction. He has no faith whatsoever in human systems being able to respond to this problem. I think it's slightly different. The human spirit has immense resilience. We know we can solve problems when we're faced with them. we can get to this. It is not a question that the structures we have are incapable of making decisions and responding in a crisis. We can do it. I do not accept the sociological pessimism that says it's now impossible because we only see the performance of the monolithic structures that we have. I remember that when Yves de Boer was speaking to the business community on the 11th of December in Bali, he said what we have to do is to turn round the supertanker of investment. And I thought, you know, supertankers take about 22.5 miles to stop in an emergency. They're a bit inert. And they've got one brain, the master, in that tiny little tower at the back, dictating where they go. And they are full of hydrocarbons. You turn them round and put them somewhere else, they just deliver the hydrocarbons somewhere else. We often see our human institutions as supertankers, inert, dinosaur, rigid, difficult to change direction. But you know, human institutions are made of people. They're only inert because we project authority into the institution and give it power over us. What we have to do today is to deconstruct the dinosaurs and to move from the supertanker to the shoal. You know, shoals can respond very quickly. They can respond to threat, and they work together. The signals that go between the fish are almost instantaneous. In technical terms, it's the move from rigid systems of command and control to the flexibilities and resilience of complex systems, of systems of complexity, of multiple parallel processing, of distributed intelligence, of people power, of the emergence of social ability to respond to the crisis almost instantaneously and globally. We can do it. We have the support structures and communication strategies, mobilization for lifestyle change. This is not an impossibility. It is only impossibility if you cannot imagine it and then make it happen. So I offer you from supertanker to shoal as the transition in enabling solutions for tomorrow's world. Yes, there exists a state of planetary emergency. That is not hyperbole. There does exist a state of planetary emergency. Planet Earth, we have a problem. But Gene Kranz's philosophy in the response to Apollo 13 was not to bring in some Swedish economist to work out the cost-benefit analysis of bringing 3 men back to Earth. He said, no, whatever it costs, this is a question of survival. Failure is not an option. Thank you very much indeed.